All right, good afternoon, everybody. You are here in the GPU work graphs course at SIGGRAPH 2025. We're giving a course, obviously, on GPU work graphs. So who is we? That is Bastian Kut. Right here on the left-hand side of me is a PhD student in Coburg University. Then we have Max Oberberger from AMD. And I'm Quirin May. I'm a professor for computer graphics at Coburg University in Germany. So we're teaching a work graph course here today, and that is today. And we started this project on doing research on GPU work graphs with AMD back in January 23. We got funding from the state of Bavaria. And in the last 2.5 years, we've been working on examples of how to do work graphs. In the meantime, a lot happened. So there was the first work graphs preview coming out in June 23, and some sample code popped up. And we got Vulkan support in July. And then there was some samples coming out on GPU Open and for a game developer conference in 2024, the first official WorkGraph 1.0 release came up, and there we made this, as a team, this demonstration that I'm show you in a minute. We condensed our results into an academic paper at High Performance Graphics in 2024 in Denver, and most of the achievements that we were able to make were due to mesh nodes. There were a bunch of blog posts coming up, and there's, in fact, Vulkan mesh nodes. But we're going to talk about this further down the line. So next up, Bastian and Max are going to show you the demo that we did for GDC 24, and that should demonstrate some of the features that we have in work graphs.
1, 2, 3, hello. So for our GDC demo, we augment a scene in real time using work graphs. So here's the scene without this augmentation. And in fact, the rest of the scene is also rendered with work graphs. So if I disable work graphs, that's the scene. And we did a couple of examples for procedural generation. So one example would be the meadow generation. So everything you can see here is generated in real time. Another thing we do is we generate procedural ivy on existing geometry, and also this runs every frame, so you can like edit it and stuff. And the third example we have is a procedural marketplace generation, where you can like have a recursive problem, and we solve it using work graphs. And this all generates in real time, as you can see.
All right. So that was that. So with this GDC demo that we did in the HPG paper, we raised some excitement in the community, and we got invited to teach a masterclass at Graphics Programming Conference, which is a nice conference in Breda, Netherlands in 2024. And this is where we tried out our first version of the WorkGraph Playground app that we're going to use here today in this class a little bit. We're going to have some little bit of a hands-on session. And don't worry if your laptop does not support work graphs. We have software emulation in it. It's super easy to download. So what I would like you to do, if you haven't done so far yet, is to go to this little page up here where it says https wgpa.short.gy, and that will redirect you to a GitHub repository, particularly to the download section. And we have prepared some binaries for you to set up like in under a minute. So just download the latest release. That would be the WorkGraph Playground version 1.1.0.zip. And download that, unzip it, and just go straight into the folder. That's the fourth step here. And right here, open the folder, and then just double-click on WorkGraph Playground exe. It's all open source. You can download the source and build it yourself. Might take a little while. Right, and then you can double-click on the exe, and you should immediately see our playground here. And if not, you get a weird or a very meaningful message, in fact, on the console where it says, well, I could not create a D3D12 device. Please run download warp-adapter.bat. This will download the latest version of the warp adapter, which is the software emulation for Direct3D12. So those are the 6 steps you should be doing if you want to participate in the little hands-on part that we have. If you have a Windows 10 or 11 computer, that should work. Don't worry if you have don't worry about the GPU. We have warp emulation here running. There's a little poster. It's over there that explains everything. So again, it's basically a copy of this slide that you see here. So be sure to do this and be ready in about half an hour for a little experiment. If not, you can just look at the tutorial code as well and walk through it with us together. So okay, so after this class we were going back into our lab and designing our next demo, which we presented at GDC 2025, where we generated vegetation. You'll see in a minute what's going on there. And we, again, condensed our result into an HBG paper this year in Copenhagen. Here is the live demo.
So yeah, this is the other GDC demo we did for this year. And as you can see, we generate vegetation, mostly trees. And as you can see, these trees are very detailed because everything is generated in real time, and specifically for the next frame. And that has several benefits, including animation, and these sort of things are very easy to do this way. We also have seasons, as you can see. And you will later learn in the second block of this course how we did this.
Right. So this is all done in real time, as you've seen, and it's been 1.5 years since the first initial release of work graphs. And our goal here today is to teach you how you can use work graphs yourself. And this is our schedule here. So we're right in the introduction and foundations part. After that, we're going to talk about the concepts of work graph and then have a short break. And in the end, we're going to talk about advanced work graph stuff. So that's going to be some material shading, recursion, and then Bastian is going to talk about procedural generations. This is really advanced stuff. So this is what you can do with work graphs. And then Max will later explain how work graph, a possible work graph implementation could work on a GPU. So let's get started with the first part, introduction and foundations. So why do we even need work graphs? Why is that something that I should concern about? And there are some alternative approaches to work graphs. Why shouldn't we use them? And we're going to dig into this, but before I really want to make sure that we're all on the same page and explain some GPU concepts that hopefully many of you are already familiar with. But those concepts, we're going to show how you can put them into work graphs. They're, so to say, the cradle of work graphs, if you will. And you probably know those concepts already, but let me repeat them real quick so we have a common point of view here. So it's a very good idea is to do this to explain on GPU this in the GPU history. And so we have work graphs, which is you can consider as an evolution in the step of programmability in graphics hardware. And if you mention programmability in graphics hardware, you should always start with register combiners, which many people believe are the first attempt to do that. Programmable vertex processing came in 2001. And then we had the shader model too, which is considered to be the first fully programmable vertex pixel shader pipeline. And it's really important even today. And it got augmented by dynamic flow control, and we got geometry shader hardware tessellation later on. And then something happened which is called GPGPU, which generalizes the computation or the capabilities of how we can use GPUs for tasks other than graphics. And CUDA was a big step in this direction in 2007. And then hardware tessellation came, and compute shaders were added to Direct3D, which standardized, in a way, the programmability of GPUs. A very important thing, and you'll see that in a minute, is execute indirect for work graphs. I'll talk about this in detail later on. And then there's obviously a hardware ray tracing, But for work graphs, more important is the other feature that was kind of like shadowed when hardware ray tracing came up. This is mesh shading. And those, so I faded some of the concepts here of some of the historic milestones there, and to show only those which are important to the evolution of work graphs. So to start off, the shader model 2.0 is very, very basic, so we still use it a lot today, as you'll see in a second. So we have the graphics pipeline with a couple of stages. We have a simplified version of that, and you should all know how this works. We have a mesh, we input this into the pipeline, the data propagates through the pipeline, and we get a discretized set of fragments. So how does this work? So we have a vertex buffer where we store all the attributes of a vertex. I color-coded them so you can match them with the mesh over here. And then we have the connectivity or topology where we put into our index buffer. Here we have triplets of indices, and every triplet of indices forms or specifies a triangle. So what happens is that the input assembler demultiplexes the vertices and then reads from the vertex buffer the corresponding attributes. Here it's four-dimensional positions. And there we already see a little concept here, is that everything seems to work in parallel. So every little step here can happen in parallel. We have a high degree of parallelism. And that's also something which is very important for work graphs. A little bit more important is the next stage. It's the vertex shader stage, and where you as a programmer could write program code. You would specify how your input data structure would look like. Here is vertex in. It's a four-dimensional position. And the entirety of these vertices would go through the vertex shader. However, you as a programmer would write a little function here, vs main, which would specify how you would transform every vertex. So that would consume the input vertex. You would do some arithmetic with it and output it, the transformed vertex, into a special output vertex data structure, and eventually return it. And here, everything happens in parallel for all vertices at the same time. So you have, and you should be familiar with this concept, you have the same instruction, a single instruction applied on multiple data items. And this goes by the name SIMD. And why is this already important for work graphs? Because we consider the SIMD concept, this D here, as a work item. So you consider every of these vertices that you put in and you output as a work item. And the input assembler up here you can consider as a producer, and the vertex shader here as a consumer. Or likewise, the vertex shader can also be a producer producing new items. So the concept of work items is part of work graphs. It's already in the name. So what's next? So next we have the rasterizer stage, and there we have to go back and see how the topology looks like. We have essentially three vertices that form a triangle, and they are now a work item, and they go into the rasterizer, and the rasterizer takes this work item and creates 12 fragments. And by this it does something which is called amplification. So it amplifies one work item to multiple work items. Here, these 12 bluish fragments. And likewise, we could amplify this red triangle here from 3 vertices to 6 fragments. So this is one concept. We can amplify work. It's already there in the hardware, not yet in software, but we already got it on the GPU. And we have got another concept which is called work reduction. So if the triangle happens not to produce any fragments, we essentially reduce the number of work the GPU has to do. And then for completeness, we can repeat the concept here in our little wrap-up on graphics programming, on how pixel shaders work. So every fragment is assigned to a thread of a SIMD instruction, and then the shading happens and we output the shaded fragments. And finally, the output merger takes the discretized triangle and merges it with what's already in the frame buffer. So this is shader model 2, very basic, but still the concept that we have in hardware there is something we would like to use for work graphs and have it a little bit more flexible. And you probably all know that we classify the stages of the pipeline into whether they're fixed function or programmable. And by the time these GPUs came out in about 2002 or later, there were distinct hardware units for vertex shading and for pixel shader. So there was separate silicon for these different tasks. And then people said, hey, why don't we just transform vertices and pixels? Why don't we just add other stuff on it? So we have SIMD for vertices and we have SIMD for pixels. Why not just have SIMD for geometry or for primitives? And this is where they came up with the idea of geometry shader. And then they said, we've got lots of SIMD here. Why don't we abstract this away and make a unified model? And this is where they came up with the unified shader model in 2006. And they basically said, OK, let's consider a GPU as a bunch of shader cores, which you see down here. So we have a little part of a GPU with 16 shader cores. We put it together in what's called on AMD a work group processor. And we attach some shared memory to this. So in the RDNA 3 architecture, we have about 128 of those shader cores per workgroup processor, and that memory down here is 128 KBs. And if we take a bunch of those workgroup processors and put, let's say, 30 onto a GPU, we have an RDNA or an AMD Radeon RX 7800 XT. And we add some device memory, which is in the order of several gigabytes, and we have our GPU ready. So with that abstract model, they came up with the idea of doing compute shaders. Hey, let's not just do graphics with it. Let's do compute shaders. And a compute shader requires a software abstraction. So every thread is put into a grid of threads, which is called a thread group, and we add an abstract concept of a shared memory here, which is called group shared memory, and everything really maps nicely to hardware. And then we have what we call a compute shader, and you can identify those threads in a grid with a group thread ID, and you can identify each of the groups with a group ID, and then you can program them pretty conveniently. And those compute shaders become, we'll see this in a minute, very important for work graphs too. So what has happened now is that we have two coexisting pipelines, a very simple one, the compute shader, and our, pipeline, a graphics pipeline, which gets more complex. So the compute shader is, you can program it relatively easily. All you need to do is you need to write some shader code for this, very similar to a vertex shader, except for that you have to identify what group you're in or what thread you are within your group. You must specify as a programmer how many threads you would like to have per group, and then you can compute what work item you want to work on, read it from the buffer, and have access to the device memory over structured buffers, for example. So this is how a compute shader works, and as said, it's going to be a very important part for work graphs too. So, what were we able to do with compute shaders? Let's consider the following problem here. You have a bunch of objects, let's say 10,000, and you would like to render them. And obviously, you will probably not see all 10,000 objects. You might want to cull a bunch of them. So you would have a compute shader that would, hopefully in a parallel fashion, determine what object is visible and what not, and then write out the visible set into graphics memory. And then with that visible set, so basically let's assume we have culled 5,000 objects, so 50%, we kick off our graphics pipeline, and the graphics pipeline would read those 5,000 objects and create a discrete image out of these 5,000 objects. And then maybe after that, you're probably not happy with your image. You need to do some post-processing. So you're going to kick off another compute shader, and then you're going to read the image you just created into your compute shader, do your post-processing, maybe anti-aliasing, a depth of field, and then write the result back to memory. And there we have a bunch of problems. There are these barriers, which basically synchronize the different stages, though we can't kick off rendering down here before we've done the culling or finished culling, and we have to make sure that our image is fully generated before we can run post-processing on it. This is the first problem. But the second problem is a little bit more severe, I believe. It's the constant reading and writing to graphics memory. Then you might say, oh, okay, graphics memory, I know that's fast. I mean, compared to the other parts that I have in my system, for example, the CPU has about 64 gigabytes of gigabytes per second that it can communicate with GPU memory. And if we want to transfer memory from CPU to GPU memory, it's even slower. And the GPU memory bandwidth is about 1 terabyte per second. That's really huge, you might think. The problem is not that it's big. The problem is the growth. Because if we compare it over the years, so we have an axis over the last couple of years, and have a normalized scaling here in terms of performance. So the GPU performance compared to this year here in the mid-90s, it has grown exponentially here. This is a logarithmic scale here. But the memory bandwidth speed couldn't keep pace. Its slope is significantly smaller, so that means we can always compute so much more than we can get memory for. Well, that might leave our computational units that we have here idle, and that's bad. And this is not a 2025 problem. This is a problem that we've always had. And this is why the compute shaders had already shared memory, and they were connected to the compute units up here were connected with a low latency memory subsystem to the shared memory, so you could work as local as possible on your data. So this idea is something that they tried to exploit using hardware tessellation in a way. And this is another stage in the pipeline that we added, or that the people added here right after the vertex shader. And hardware tessellation is some sort of geometry amplification. So we have, here you can see the control points of a bicubic Bezier patch. So those are 16 control points. And hardware tessellation aims to sample this into a much finer set of triangles directly on chip. So basically, attempting not to do many global memory round trips. So everything should hopefully nicely stay as local as possible in fast memory parts. So this was one attempt. Works great, for example, for subdivision surfaces. And a little bit more sophisticated or more flexible in a way is mesh shading in 2018. And this is also very important for work graphs, because mesh shading is a part of work graphs effectively. So what does mesh shading solve? So going back to our little example of these 10,000 objects that we would like to cull, and 5,000 survive in our little example. So we have the compute shader. We read the 10,000 objects and write back the 5,000 that are visible, and then we kick off the graphics pipeline. So why don't we just save this trip, or this memory trip back when we write out these 5,000 objects? So why don't we just go ahead and directly write to the rasterizer, right? So we input 10,000 objects here, and we output only the visibles. That is exactly the idea of a mesh shader. So the mesh shader basically replaces all that part here in the pipeline with a single or two stages, as you'll see in a minute, and just simply writes it out. And the mesh shader effectively works like a little compute shader. We have our group thread ID as before, we have our group ID, we have our number of threads, and now we have to tell the rasterizer what kind of topology it is able to consume. And then we output a little small vertex buffer with up to 256 vertices and a small index buffer. And we can use the term meshlet. I think this is the French diminutive for mesh, like little mesh. And that's what we output for each mesh shader work group. And if we have multiple work groups, we output multiple meshlets. And it could work, for example, like that. You have this big model here, use a pre-process where you would subdivide your mesh into meshlets. So here you can see the nice meshlets that we have, and we upload them on the GPU. The mesh shader does the mesh shaders do their job, and then they output the transformed vertices and then sending it to the rasterizer. Works pretty nicely, and we have a little blog post on that on GPU Open, an entire series actually on this, how you would program mesh shaders. And as said, they are important part for work graphs. So now we repeated the GPU concepts for work graphs, and I hope we are now all on the same page. A little rush through the history of graphics. But why do we actually need work graphs? And to answer this question, we need to look at a concept which is from 2015, which is called execute indirect. And with this flexibility of compute pipeline, in conjunction with the graphics pipeline, execute indirect became necessary. I'll show you how that works in a minute. So just going back to our little problem of culling objects. So we have a little GPU problem that we're running over time. And again, we want our compute pipeline to determine what objects are visible or not. So we read out the 10,000 objects and we write out the 5,000 that are visible. And then there comes the graphics pipeline, which is supposed to render them. So we need the barrier here to synchronize these two dispatches, if you will. And then we kick off the graphics pipeline. And the graphics pipeline will read those 5,000 objects and write it back, and then go on with the remaining part of the pipeline or the next frame. So what's the problem here? The problem here is that we somehow need to say how many objects do we actually want to render. So we got to write out the number of objects into this variable n, and the data, of course. But then the consumer has to know that number. And that's a problem because we have to communicate the number n from the GPU to the CPU, and therefore we require a fence, which is a very hefty synchronization primitive. It synchronizes CPU and GPU. And that's very expensive. So after that, only after that, we can kick off the consumer here, which is our draw call. With execute indirect, however, we would only make sure that we know that the CPU knows the memory location of this guy here. This is the little ampersand here. So CPU and GPU agree on the memory location where this n in the data is written into, and we pass this to the producer so the producer can do its job. And then there's no need to read this data back because we can be sure that this number n is written into this memory location that we agreed on. And therefore, no fence is required, and we can kick off the draw call right after without any fence. So this is what execute indirect does. However, we still have the barriers here. And this is a big problem. What can also happen with execute indirect is that we can have empty launches. Just going back to our culling example here, if we look in the wrong direction, we might see none of the objects. So n might be 0. But we don't know this. We have only the address of n. We don't know the actual number. Therefore, we still got to kick off this consumer draw call here, and that's an empty draw call, and that's, well, you still pay the expensive overhead of a draw call. And things can become a little more dangerous too, because we don't actually know how much data we are going to require. We have to be prepared for the situation that we have 10,000 objects, right? But we do culling because we anticipate that we're not going to render 10,000 objects, but we are probably hoping to render a significantly smaller portion of that. So there's going to be some output and there's going to be some unused memory, but we have to block this memory. There's no way around it. And even worse is what could happen is if you are, well, doing some gambling and you say, I don't want to waste all this memory, you might actually end up into overflow and other problems that you need to handle at some point. So we always have to, so those are the four problems that we have. So we have this little pipeline, and I mentioned earlier, well, we still have the mesh shader pipeline, so let's add a little producer to the mesh shading pipeline, which is the amplification shader, and the amplification shader can exactly do that. It can do some culling. The problem is, however, that it's graphics only. So you gotta have a rasterizer after a mesh shading pipeline. And what it cannot do, it is a two-stage pipeline. There's no self-recursion or something like that, or there's nothing like a longer change. We cannot add another stage to the mesh, to the pipeline here. Or even have something like multiple stages or parallel chains of that, or something like a branching like we need for the classify and execute part that we're going to talk about later. So those are all the problems that we could solve with execute indirect, but not with mesh shaders. And still we have the compute shader problems that I talked earlier about. Those were the barriers and the device memory I/O problems. So all these problems are hopefully solved with work graphs. And so I hope you got your attention on work graphs now, so please make sure that you have downloaded the Work Graph Playground app. What you can do now is you can open up an editor in the Work Graph Playground folder and follow us. If you have any questions, just raise your hand and we'll walk around and assist you with your Work Graph Playground, but we already tested it on my students. So here are some useful commands that you can use, but we'll dig into that a little bit later. If you open up tutorial 0 here, you can see a HLSL shader code. If you do not like the comments here, and probably you don't need those comments, in class here today, you can use your editor to fold the comments together. The comments are very verbose because we hope that you, or we designed this Work Graph Playground for you to do at home alone without our help here. But today you have lots of help here with us, so you probably find them a bit disturbing. So this is something that might look a little bit more better for you. The next thing is we all love to code with friends, so and interchange with each other. So please make sure to go on AMD Developer Community Discord channel, discord.gg/AMD-dev. We have a little QR code here on the left side, and I'll make sure you can see it while I walk through our course agenda. So I'm getting a little bit ahead of time. That's great. So we got more time for concepts, notes, records, and launches. And I'm going to give it over to Max for the next thing, and I'll be walking around with Bastian to see if Work Graph Playground works for you.
Yeah, round of applause for Kuhn. Let's thank him for the great introduction. Let me quickly switch slide deck before we can start with our first concepts, which is, as you can see, the Work Graph nodes. So, as Corinne just mentioned, before we can discuss nodes, we maybe might need to look back on what we had so far. So far, when we did some work on the GPU, we had these dispatches. Let's say we're just doing some compute, so these will trigger some sort of compute kernels that we wrote earlier. And to sort of have the GPU execute them, we have to submit those to the GPU through what's called a command list. The emphasis on here is really on the list part, because this is just one long list. As Corinne mentioned, there's no sort of branching, no sort of conditionals, no whatever. And that sort of limits our flexibility for all of the sort of fancy stuff that we showed in our demos before, because those heavily rely on sort of being able to dynamically launch work or other things, or for example, do recursion. So what can we do now? Let's just say, okay, we want something new, we want work graphs, so let's just replace all of these commands with just a single command, call it dispatch graph. So what does this dispatch graph look like? So underneath, it's no longer just a simple compute kernel, but it's a series of compute kernels called nodes. These are still very much similar to, or each of these nodes is still very similar to sort of one compute shader kernel, and we'll see what these are in a minute. But the nice thing is, this isn't just a work list, this is a work graph. So we can sort of turn this into a full graph now. For those sort of on sort of fancy graph terminology, this is a directed acyclic graph. So we still sort of have a sort of flow of execution. In this case, this would be sort of from the left to the right, where sort of each node triggers another one, and so on and so forth. You can already see, for example, that one node can trigger multiple nodes, or multiple nodes can trigger the same node. So really a lot of flexibility there already. There are some sort of small limitations to this. For example, the longest chain of nodes in your graph is limited to 32. This sort of helps you prevent your GPU from like being overloaded with work. So we sort of limit the depth of the graph. As the name sort of for work graphs implies, this all is based around concept of work flowing through this graph. So let's now look at how we can do this. So instead of sort of triggering one kernel directly by sort of calling dispatch or whatever from one node to the next, we instead sort of send small packets to each node. Those packets are then sort of would trigger execution of the node, and the node will then sort of process this packet. And we call these packets records. You already sort of saw Kiran talk about work items. So we can think of this being very similar to, for example, if you have your vertex shader output some sort of vertices, those will then be sort of processed by the rasterizer. So in this case, the node on the left sends a record to the next node, and then that node has to process it. So again, we sort of have this consumer-producer relationship between these nodes. And as this is sort of a debug graph, you can already see that each consumer can also be a producer, similar to sort of what we've seen before with the consumer-producer model in sort of the fixed function vertex pixel shader pipeline. Now, one important distinction that I sort of mentioned before is that these records are sort of just indicating that we want to run this node, and obviously it will run eventually, but these are not directly dispatches. Instead, you can sort of imagine that there is sort of a virtual queue attached to each of these nodes, and then the sort of work graph runtime or the work graph scheduler will wait for sufficient work to be available for this node before it then executes it. So you don't sort of directly dispatch the next node. Okay, so with sort of this whole execution of the graph being based on work, we sort of end up with a chicken and egg problem. If work is produced by sort of nodes sending them to other nodes, where does the work initially come from? And that's sort of where the dispatch graph command that we saw earlier come in, because with or when dispatching a graph, we can sort of specify some sort of entry work, in this case sort of some records that we sort of send to the first node, and that will then kick off the rest of the graph. And sort of sending these sort of initial work packets isn't limited to sort of what you could call a root node of the graph, but instead you can just send them to any of the nodes in the graph, giving you a lot of flexibility for what you want to do with it. So now that we sort of know the concepts of nodes, let's just see how we can offer these nodes. I said before that nodes are basically just sort of regular compute kernels. So if you want to follow along, Kiran already showed you where you can sort of download the work graph playground. You can already open the sort of tutorial 0 hello work graph HLSL, and in there we'll sort of find our first node. In this case, it's called the entry node. And basically, as I mentioned, nodes are just regular compute kernels. So we offer them in the HLSL sort of language as just normal void functions. But we still sort of need to tell the compiler, hey, this is a node. I want to use this for work graphs. So we just basically tell the compiler, this shader is now a node, and that's sort of it. As this is the entry node to our graph, we also need to tell the sort of work graph runtime or the compiler, this will be an entry node, and there is another one of these attributes in square brackets that you can use for this. This case is node is program entry. Next, we sort of need to sort of identify our node, because in our graph we have many, many different nodes, so we need some identification scheme for this. By default, the sort of node ID is derived from the function name that we gave our void function. So in this case, it would be entry. But also if, for example, for whatever reason you want this to differ from the function name, you can also set this node ID attribute explicitly. So here we then explicitly said, okay, the node ID of this is entry, and then we're sort of free to choose whatever name we want for our actual entry function. Lastly, sort of one remaining attribute that we need to add is a node launch type. These we'll discuss in a bit. So for now, we just write node launch red. And yeah, you can, Bastian will then tell you everything about this. You can also find all of the syntax on the small cheat sheet that we handed out. There's a whole section, or one page dedicated to node launches, where you find sort of all the attributes that you need to specify in your work graph to sort of turn any one of your compute functions into a work graph node. So before we can sort of discuss how we can run this as a graph now, let's quickly look at sort of the compilation model for work graphs. And before, if you wanted to compile a HLSL file to be used as a shader, for example, a vertex shader, you would use the DirectX shader compiler for this. You call it with sort of a target, for example, VS60 for vertex shader in shader model 6.0. And then you also specified the entry point into your shader. So you sort of said, okay, I want you to compile this function as a vertex shader. Well, with work graphs, things are a little bit different because we no longer have sort of individual shaders as sort of this intermediate library as output, language as output, but we're dealing with sort of whole libraries. So in our case, we can just compile the whole file, say, okay, in this file, there will be some work graph nodes. We use the target lib in this case. The minimum shader model that we can choose for this is 6.8, so it's lib 6.8. And as we already annotated all of our functions with the little shader node attribute, we don't need to explicitly say which entry function we need to use for this. The shader compiler will just look at all of the functions with a shader node attribute, put them in your library, and there you go. So then you may have compiled many, many of these Dixel libraries. So you can then sort of try to combine all of them into a single work graph. And the work graph, you use a concept called state objects. In this course, we're more sort of focused on the GPU side of programming work graphs, but you can also obviously, for example, take a look at the CPU side code for the work graph playground if you're interested in that as well. But just in simple terms, we may have many of these DXIL libraries, all of them containing, for example, multiple nodes. Then the runtime will go ahead and sort of try to lay them out as a graph, try to sort of make the connections between all of these nodes, and also run some basic validation. For example, here we have something that's not allowed in our graph. We have a cycle at the bottom. We're dealing with directed acyclic graphs, so no cycles allowed. And on the right, you can already see there is sort of a connection going nowhere, meaning there is a node missing, and obviously that will also sort of cause the graph to not compile. Luckily for you, you don't have to deal with any of this because the work graph playground will just do all of this for you, and we'll see some examples for this later on. So back to our node that we wrote before, it's the little entry node, and that's already part of the work graph playground in the sort of hello work graphs tutorial, and the entry node is sort of printing some hello work text. It's telling you which file to open if you want to edit this tutorial, and so on and so forth. But we're sort of here to do a work graph. So and one node isn't really a graph, it's just a single node, it's pretty boring. So let's see how we can add a second node to our work graph. In this case, we want a second node, let's call it a worker node, and we want to do this some more work in our graph. So further down in the sort of still the hello work graphs HLSL file, we will then sort of declare another function. In this case, we call it a worker function. we again need to specify sort of all the attributes for it. For example, we said we want this to be called worker, so we add the node ID for it. And then obviously we also need to add the same sort of shader node and node launch thread attributes that we saw before. And again, luckily for you, we already provide this in the Hello Workgraphs HLSL file, so you don't need to type any of these, any of this. But if this already is part of the Hello Workgraphs HLSL file, why don't we see any sort of output from the worker node? That's because in our graph right now, it just looks like this. We have two nodes, but those are just two separate nodes. They're not really connected to a graph. So next, let's look at how we can connect these two nodes together to then be able to send sort of these small records from the entry node to a worker node. And to do this, we sort of declare the output of a node as part of the sort of function parameter signature of a node. So we go back to our entry node, let's make some space, and let's declare a node output. To do this, we sort of start by declaring an empty node output. We don't really want to send any data to this worker node yet, but we'll get to this in the next part when we talk about the records. We then also need to sort of specify which node we want to target. This works similar to sort of the node ID for the function attribute that we saw before. So by default, we just name sort of this variable or this input parameter to our entry node function, in this case worker, that will target the worker node. But again, we can add the node ID attribute and then name it whatever. In this case, we name it node output. Lastly, we sort of need to tell the sort of workgraph runtime, which will try to run all of this, some more information. In particular, we need to tell it how many records we intend to send. We again will cover this in a bit greater detail when it comes to records. And also you'll see sort of at the very end of this course how this is important for the GPU to be actually able to run this. But in this case, we just want to send a single record. So we just write max records 1. Again, this is all part of the sort of template code that you can find in the Workgraph playground. So why are we still not seeing anything in our output here? Well, that's because we just sort of declared the connection between these two nodes, but we haven't sent any records along yet. So if you are in the Hello Workgraphs HLSL file further down below, you will find the sort of following commented code, which is for the node output to call the function thread increment output count by 1. What this will do is basically, as we are dealing with sort of an empty node output, we don't actually need to sort of describe the data that we're sending along because we aren't sending any data along. So we can just say, okay, I want 1 record more. So we start with 0, this will increment it to 1, and that will sort of send a record. So what you can do is in your Hello Workgraphs HLSL file, if you have that open and you have the Workgraph playground running, you can uncomment this line, you can hit save in your editor of choice, and if you have sort of the command line or the output open for the Workgraph playground, you will see a sort of nice little debug print message saying, oh, there were some changes detected to the shader source files. So the Workgraph playground is sort of constantly monitoring all the source files, so you don't need to restart the app every time you sort of make changes to the shaders. And then if you give it a second to sort of compile the shader, we now get our hello world message from the worker node down below. So we've successfully sort of launched our first node in a Workgraph. But still there is sort of some template code still remaining. It just says hello your name. That's not very nice of the worker node to just be greeting us with this generic message. So let's see how we can change this. So if we go back to the Hello Workgraphs HLSL file further down below in the worker function, you will sort of find this line where it says print a center text, and you'll find the message that we saw on screen with sort of hello your name. So you can also go in here and change it to your name. Obviously, I don't know your names, so just say hello SIGGRAPH 2025. We can save the file again. You see another message saying, oh, there's another change detected to the file. Then sort of short compile time with a little bit of drum roll, and we see a nice sort of personalized hello message from the worker thread greeting everyone here at SIGGRAPH 2025. So with this, we basically seen a few concepts already. We've seen sort of how we can declare nodes. We've seen the basics of how we can send records between one node and the next. So how we can sort of turn multiple independent nodes into a work graph. And we've also seen that sort of editing code in the Hello Work Graph Playground or working with the Work Graph Playground is quite easy. You can just change the code, hit save, it will all update for you. You don't need to do anything on the CPU side to sort of add more nodes or whatever. So we really designed the Work Graph Playground to be sort of a plug-and-play app to start experimenting with work graphs. So going back to our declaration of the node output and this sort of magic function that we've called thread increment output count. We currently have a 1 in each of these occurrences here. So what if we change this both to a 2? Would we get 2 hello messages from the worker node? Any guesses? Well, if you have the Work Graph Playground open, you can just try this out, just change both to 2. It's important to change both to 2 because if you're sending 2 records and you're told the runtime you're only going to send 1, that will cause some problems. But if you do this, hit save again, you'll still end up with sort of the same text that we've seen before. Still the same message, you'll still have your name in it, but still only 1 message, not 2. We would expect something different to happen here. But it didn't. So what's going on here? So this graph is still sort of the entry and the worker node, and we're now sending 2 records from the entry node to the worker node, but you haven't really attached any data to it. So if we look at one of these records that we're sending, it's just empty. So every time the worker node receives one of these records and runs, it will print the same text at the same position on screen every time. So basically, you can sort of launch the worker node 1,000 times, you will not see any difference. So in the next sort of concept, we'll look at how we can sort of parameterize these records to make nodes do different things depending on their input. And this is where we call querying back to stage, where he'll tell you something about how to declare records and use them in a work graph.
Okay, thank you, Max. So, work graphs concept part 2, if you will, we're going to talk about records. And to that end, here's a little bit a screenshot of our Work Graphs Playground app. And let me use my laser pointer here real quick, not the pen, the laser pointer. And then we have this little menu up here where you can select the next tutorial. So the next tutorial is tutorial number 1. It's on records. And then after you click that, you should see this little thing here. And there we essentially draw a bunch of labels. Here it says box 00, box 20, and box 30. And what I'm going to do with you is walk you through the subtasks of this little tutorial here and see how we can do that. There's going to be 5 that I'm going to be a little bit more explicit here, and you should be essentially be able to do it along with me once you have the Work Graph Playgrounds app running. If that's not the case, you can just lean back and enjoy. And but you should already be prepared for your homework where you can learn a little bit more on that. So let's recap what Max has just said. We have our entry node, and the entry node sends a work item to the worker. And that's essentially a record as part of a node output. And how did this work? We have our entry function here, and we have a node output here, and we say to the work graph subsystem we would like to send this node output to another node which is named worker, and we have declared another node here with the node ID worker here. So this is how these are connected. They're not like automatically connected, just like maybe a vertex and a pixel shader are with these stages in between, but we have to explicitly say what compute shaders are connected here. And this is done by the node ID attribute here. So now, so you saw, let me go back a second. So this was a little bit recap of the previous tutorial. Now in the new tutorial, you see up here, tutorial -1 records.h8isl, it looks a little bit differently. So first of all, we would like to send an empty node output which prints hello world. This is essentially a recap of what we just did. So we are going to link this to the node print hello world, and if you look in the code of the WorkGraphs Playground app, you'll find such a node already implemented for you. And if you would, you can walk along with me and emit a single empty record to the print node hello world here. And here we have a little bit of a different situation as we had before. Because in the previous tutorial, we had a single thread for the entry node. And up here we have essentially 4 threads. So those are 4 threads that run simultaneously on the GPU. This is a different launch mode. We're going to cover launch mode in the next concepts section. But just imagine this is a regular compute shader with 4 threads. Very thin, but still. And if you would go back to the first tutorial and say, hey, in the last tutorial, just use thread increment count, thread increment output count. I want to output 1 record. That's not going to be the correct solution. In fact, it's going to be wrong because we're having 4 records. And what happens is that every thread here, every of these threads, we have 4 threads, would like to output a record. However, the problem is that we're having only 1 record that we can output. And the semantics behind this max records here is that the entry function as a group of threads, as a work group of threads, outputs at most 1 of those records. If we're having 4 threads running, this would essentially mean that the totality of these 4 threads will output 4 records, and that will break the promise that you made up here. But luckily, there's a solution to this already implemented. There's a method on the empty node output which is called group increment output count. You still can pass the parameter 1 here, and that will tell the runtime that the entire thread group is outputting a single record. So that would be the solution of the task 1 to use group increment output count. So in that you have learned another function that you can use. And to put this together, or to summarize this, if we have like an entire thread group, as we have, for example, with compute shaders, we have the same concept with work groups. Every of those wiggly lines here represents a thread. And if we would call thread increment count every wiggly line, every thread would output a new work item. However, if we use group increment count, 1 particular thread outputs a single work item as a representation, for the entire, as a representative of the entire work group. Okay, you can look at this. We have this little concept here summarized in our cheat sheet that we placed out for you, and you can take them home and you can download them also from our webpage. Turn onto the page record output, and there you can find on the lower left a little bar which discusses empty outputs. So there are these 2 concepts here of group increment output count and thread increment output count, nicely summarized. So if you add this little line, group increment output count 1, you can finally see hello world without the red box. But we're going to need this group increment output count for your homework. So bear in mind that you keep your cheat sheet and take it home. Okay, so we got the first problem solved. The next problem is we would like to look at how, and this is actually already part of the tutorial as some sort of a helper solution, how these individual box labels are written out. So how do we manage to write out these box labels here? So what we had before is a single entry node would be capable of sending some anonymous or empty work item to the worker. And now we would like to add some data to it. And one way of doing this, if you would had the task to design a work graph system, you would probably come up with a struct. So in a struct, you would define this data. And here in our particular case, in our problem, we are defining a struct print box record, and it has two members, integer to top left and an integer to index. And the top left basically indicates the upper left corner of where you would like to print the box, and the index basically encodes these tuples, or this pair of numbers. Here it's 0, 0, here it's 2, 0, and 3, 0. So, and we're all going to encode this data from the entry node, and the entry node will send out this work items, the node outputs. And now I'm going to explain you how this is working in work graphs. So we have our entry node here, and we must specify essentially 3 things in our entry node when we want to output records. First of all, we must specify that the entry node can emit such records, and we do this by the node output. And we have this little angle bracket template type of argument where we put the record type that we just defined. And this is what we're doing here. Then we must specify what node is going to consume those records, and this is going to be our print box node, which we have defined further down in the code. And you can look at the code. It should probably fit on 1 or 2 code pages if you collapse the comments. And then you can see the node. And the last thing that we have to do is we have to provide a number of how many records we would like to output at most. And in this case, we're having 4 threads, so we're very conservative. We promise not to output more than 4 records. So at most, this is a little side condition here in the work graph specification. You can output at most 256 records. So you may not exceed this, this number here. And you can have at most 1,024 outputs, including the empty node outputs. And you have to make sure that you're not going to surpass the memory limitation of 32 kilobytes where these nodes can communicate and share data in between. So what we see here is that this node is now capable of sending out 4 records to the print box node. But what we haven't seen is how it's actually happening. And the way that happens is we are, first of all, going to write this little bit longer line, and I'm going to walk you through this line here. So first of all, we're taking this box output parameter here, which is where we would like to send the outputs, and we call our member function, which is called getThreadNodeOutputRecords. And this is basically returning a little array, if you want, of the output records. And this parameter here says how many records you would like to have per thread. So I have this predicate has box output record, which determines, which is my predicate, which determines whether I want to output something for this thread or not. It's either true or false. When it's true, I want to output 1 record, and if it's 0 or if it's false, I don't want to output any record. And then I have a little handle onto this, which I call box output record, and it's of this type here, which is thread node output records with the parameter, with the template argument print box record here. So a lot of code, yeah, but it's just necessary to do this. And the thing is, what GPU experts probably, or experienced GPU programmers are probably understand immediately, but less experienced people are probably going to have trouble, is why I'm using this funky tertiary operator here is because remember we have 4 threads, and these 4 threads, they go in lockstep, so they are executed at the same time, and you have to be sure that this part is evaluated in a thread uniform way. So if you call this function getThreadNodeOutputRecords, please make sure that it does not happen in different branches of your code. But prefer using this tertiary operator, for example. Once you have that in your hand, this little array, you can fill this array. In our example, we have 1 array per thread, and we can access the element of this thread local array either with the getMember function on this box output record here, and then just access the members of the struct that we defined earlier directly, or you can also use the angle bracket or the bracket operator. Okay, once you have this, everything gets packaged into this work item, and we can send it off with a box with the output complete function here. Right, and you can see that again on the record output part, on the record output page of our cheat sheet, and then refer to the right column, and there you can see how you can output data pretty concisely. So now that we output the data, this work item is sent off, and hopefully it arrives at the print box function. However, not yet. We still have to do something. So, and if you change your code there and you hit Control S, you get an error there. And in our work graph playground, it's not very verbose. It says this here. And to that end, we have a little debug mode here that you can enable with a command line argument. So if you start the work graph playground with the enable debug layer, it will add a little bit more information. And then, in fact, we just spew out the error message that we get from Direct3D, and it says, okay, something went wrong. And if you decipher it, it says, okay, the output record size is 16 bytes, but the target node expected 0 bytes. So be sure that these are matching. Yeah, and in fact, this is the problem that happened here. We have our print box has no notion of a receiving record yet. So we have the thread node input record. So to fix this problem, you have to add the thread node input record variable with a template argument of the record that we defined, and we give it a name, and then we can receive it. Right, and after receiving it in your code, you can get the record and basically take it out from the input record here, and then you have direct access to the members of the record. And then you can do whatever you want to do in your code, and here we do some writing. Okay, so that's one thing you have to be aware of, that the records that you send around must match in size. And here's a little pitfall that can happen. I said they have to match in size. So here we have an int2, which is 8 bytes, and another int2, which is another 8 bytes. So we have a total of 16 bytes here. And if we, for some reason, have another struct here, which happens to have the same size here, it would be totally okay for the work graphs playground, or sorry, for the work graph system. And they would probably not detect this error, and you would probably get really funky error messages here. Oh, sorry, funky behavior, not error messages, unfortunately. So to sum this up here, how you can receive and send records, you can look on the launch nodes page, and in the column of, thread, and that summarizes the concepts of how you can receive data. So next up, I'm going to walk you through how you would probably do the solution for draw rectangle record. So the next problem that we're having is we would like to have these little boxes around these labels that say boxes here, and therefore we have to first declare a little rectangle here. So a rectangle record, which would specify the dimensions of the record here. And if you go through the code, there is a little helper function that we predefined in common.h that will actually take care of the drawing, but it's a function that you have to call, and you have to parameterize first. And therefore, what you got to do is you first have to define a little struct, which I call draw rectangle record here, which essentially lets our entry node configure the top left corner and the bottom right corner of our rectangle, and I want to be able to control the color of our rectangle record. So once we have that, we can go ahead and receive the draw rectangle record in the draw rectangle node. So this is a node. You can see this here in the attribute up here. And there in task 3, you can declare an input that would consume your new struct, and then you can use this new struct here. So what you can do is maybe look at the cheat sheet and the thread column, and the thread column will then basically tell you, oh, I can use here the thread node input record of this particular type as a little hint, and then you can go ahead and copy that simply over into your solution. And once you have this here, right, here's the little record that you put in here. And once you have this, again, refer to this cheat sheet over here, and there you can see how you can consume such a record with a .get function. So all you got to do is call the .get function, then you have the record in your hand, and you have actually the actual record right here, and then you can configure a drawRect function that we already provide for you with the appropriate data. So here I give a thickness of 1 because it's not in the record, but the remaining data I get from the record. So this is how you can consume the data from a record. So if you want to do this at home or you want to walk along with me, you're invited to do this. But if this goes a little bit too fast for you, we have something for you. In fact, we're having here in the tutorials, starting from 1, we have the records.hlsl here, where you would type in your attempts of solving the problem. And there's also the assignment descriptions here. But if you are a little bit or if you get stuck or impatient, we have some sort of solution lying next to it, and we defined the solution such that you can compare it side by side with your side-by-side comparison functionality of your editor. You can really see them side by side, what's going on, and peek what's missing out, maybe what you've done wrong, and just like a Git diff. Okay, so this should ease everything up for you, and we have these for the other tutorials. So next up, we would like to declare an output part in our entry function. So what we would like to do is we would like to output the draw rectangle record to the draw rectangle node. And to this end, again, I would like to refer you to the cheat sheet in the data outputs part, and there you can see how you can output the nodes. And here in this part, this type B is going to be our draw rectangle record here, and we would like to output at most 4 because we're having 4 threads. We want to send them over to the draw rectangle function, and this is our type here that we would like to output here in our parameter. And then once we declared it, we're finally able to emit records, and this is the task 5, and there please refer again to the cheat sheet on the data output outputs cheat sheet box, and this would be the solution. So we only output 1 if we have an output in our thread. So this is very much the same as we did before with the labels that we printed. This goes side by side. And then when we have it, we can configure the member elements of the record. So there's, if you look around, there's going to be a thread box position variable already defined in a box size, and you can choose whatever color you like. And be sure to call the output complete, and then you have it. So this would be the solutions for the work graph tutorial 1. And what I'm not showing you, but I think you can do as a homework, is like drawing an enclosing rectangle around all these boxes. There you have to remember that we already talked about this early on, that we have multiple threads in our thread group, and you can send either one work item to receiving node with per thread, or one for the entire thread group. And this is something you need to use in the last assignment, and I think you should all be able to do this with a little bit of patience. So that concludes my part on records, and we are now going to do the next concept, which is launches, and this is going to be Bastian's job.
Right, this is the last concept before our short break. And so you've already seen it a little bit in the previous tutorials. This is about the launch modes. And we will again have some tasks for it, but these are mostly your homework, so I will go over them very quickly. All right, so in GPU work graphs, there are 3 different launch modes. There's the broadcasting launch mode, the thread launch mode, and the coalescing launch mode. And probably for you GPU programmers out there, the broadcasting launch mode is the easiest for you to understand because it's very, very similar to how you would launch a compute shader. So this is how you declare the launch mode up here after the shader node attribute. And to the broadcasting launch mode, there's always connected the kind of input. So the input of a broadcasting node is a dispatch node input record. All right, and now we do the stuff that you're used to with compute shaders. We declare the size of a group. So here we get an 8x8 grid of threads. And what is new here, up here we declare the size of the grid of groups. So in total, when we launch this node, we will get a grid of 6x6 groups of 8x8 threads. So yeah, this is equivalent basically to how this would look like with a compute shader. All right, and in our tutorial, we draw these boxes. And using the grid of threads, a group of threads. But as you can see here, in between these boxes, there are some gaps. And your task will be to close these gaps. Because right now, the grid that we launch is static. And to kind of close these gaps, we have to launch a dynamic grid. So let's see how that works. So what we want to do is we want to be able to change the grid of groups that we launch. And for that, this number that we want to define, we want to make it a part of the record. And here there's a new semantic in HLSL called the SV dispatch grid. And you just add a new member to the record struct, the rectangle record here. And when you into this value, you can write the grid that you want to launch, similar to what you would write in the compute dispatch command with compute shaders. So when you want to have this dynamic grid, you have to change this attribute a little bit. It's no longer the node dispatch grid, but it's the node max dispatch grid. And so here you have to put the limits of your grid for each dimension. So here we said, okay, our limit, the maximum that we will ever launch or put in this value in the record is 16 by 6 by 1. So, and when you do that in your homework, hopefully your solution will look like this. You have no longer gaps in between your rectangles, and you have completed task 1. All right, so let's continue with the next launch mode. In my opinion, is the easiest to understand for people who have never done a compute shader, but maybe a vertex shader, because it's very similar in how it works. So here is how you declare it. You write a thread instead of broadcasting, and we have again a connecting input type, the thread node input record. And for the thread launch mode, you get one thread. The stuff that happens with the groups, you don't need anymore or you don't see anymore. So here, one thread receives one record. But there is no such thing as threads on a GPU, right? Or no single threads. They all have to run in a lockstep fashion, a SIMD fashion. So if you would think, okay, if we have a thread node launched in thread mode, there's only one thread working, all the other threads are not doing anything. But with GPU work graphs, there's a trick. GPU work graphs will try to find multiple records of the same node and cluster them together, and then tries to fill a thread group or a wave or whatever. For example, it will try to find 32 threads to combine into a group. And this all happens transparent to the programmer, so you will not notice it. You can try to find out whether this is happening by using wave intrinsics, but this is undefined behavior, so have fun with that. Okay, so this concludes the thread launch mode, and so for the broadcasting, you can launch per record multiple or a grid of thread groups. And for the thread launch mode, you can launch per record a single thread. Now you could think, okay, these are two extremes, maybe there's something in between, and this is where the coalescing launch mode comes in. And here you will launch one group of threads, but this group of threads will get a varying number of records, which we will see in a second. So here we again declare, okay, our node launch is now coalescing, and here is our input type. It's now the group node input records, and you can see up here we declared a maximum number of records. So the plural here, the group node input records, is intentional because here we can get up to 4 records for a group. And what we can do now, we can ask, hey, okay, my group is launched now in a grid of 4x4 threads. How many records did I actually get, right? It's the maximum number of records. We're not guaranteed to get that. So we ask, okay, we get the number of records that we actually got, okay, input.count. And now we can do our own thread allocation. We can basically say, okay, our first 4 threads work on the first record, our second 4 threads work on the second record that we got, and so on. So for example, if you have like a color to work on, maybe an RGBA value, you could allocate the threads like that. And all other threads that didn't get a record just exit early. Another thing we can do is we have in the group access to multiple records, right? The group can, all the threads of the group can access all the 4 records that we got here. So one special thing that we can do here, and we will later see an example of that, is we can combine multiple records into one. And this will be useful later, as I mentioned. Okay, and in your tutorial, we will do that, or in the tutorial, we will do that. So we have a node, the merge rectangle node, and this node should get 2 rectangles, and if they are next to each other, they should be merged into one rectangle. Then we want to draw that one rectangle. And this will be your task. So we have, again, these boxes that we draw, and if 2 boxes are next to each other, we can draw them in one dispatch, right? And that's your task to implement. And once you're done, you might see some flickering. Second, when you're done. All right, and once you're done, you might see this flickering. And this is intentional, okay? I hope actually that you will see this flickering, because then you will hopefully understand an important concept about the coalescing launch mode, because it's in fact undeterministic. So this is how ideally you would get all the records that you have declared. For example, you declare 3 records, you always get 3 records, but that's not the case. Actually, the order of records is undeterministic, but also the number of records you get. So there's no guarantee whatsoever whether a group is launched fully with all the records declared, or whether 2 groups are launched. There's no guarantee for that. So please take that in mind, bear that in mind when you use the coalescing launch mode. All right. So, in summary, we have 3 different launch modes, and they all have different use cases. All right, So in this session, you have learned a couple of concepts about work graphs. So a work graph is a GPU-driven producer-consumer network that has a data flow with records and has different launch modes. We will now have a short break. I think we are a little bit ahead of time, so let's set that break to 3:45, and I hope we can see you back soon.
All right. It's 15 minutes to 4 p.m., so we'll be back with our WorkGraph course. And this time, in the sort of second part of the WorkGraph course, we're going to look at some advanced uses of WorkGraphs. We already teased that Bastian will be talking about the procedural generations. But first, we need to sort of get a few more sort of quick concepts out the way that we'll be using for the sort of advanced WorkGraph section. The first concept we'll be studying on the use case of material shading, which is sort of one ideal use case for WorkGraph. And to be able to understand this, let's just first discuss what is the problem with material shading. So in the WorkGraph playground, we actually have a tutorial on this, so you can do this coding at home, but we'll just sort of do a speedrun version of this here. In this tutorial, you will see this sort of small rendered scene. We have 3 different objects here, sort of the background, which isn't really an object, it's just the skybox, as you might say. Then there is a plane, and then there's a sphere, and those all use different materials. So we can sort of show this with different colors. And the problem is if you have different materials and you just sort of try to shade them in line is those materials could have sort of vastly different complexities. For example, the skybox might just be, okay, let's return a single color. And then for the sphere, well, there might be, for example, a lot of code. And the problem is not really just that there is a lot of code, but there also might be different resource allocation. So that code might use up, for example, all of your registers where, as you can see, for example, the background color is very simple. So if we sort of want to examine this problem, let's just look at sort of a Corsa view, showing like the full 1080p resolution with individual pixels would probably kill PowerPoint and what probably wouldn't be too illustrative here. So we just use this Corsa resolution. And we said that we want to run sort of shading code. So let's remind ourselves we can only run sort of code on our GPU hardware. This was sort of the abstraction that we had before. We have like the different threads bundled in thread groups with like the shared memory. So let's just pick one of those thread groups and just make it even more simpler by just saying, okay, we have 4 threads. And those 4 threads we can sort of map onto 4 pixels. And those 4 pixels can then sort of start processing all the pixels on screen. For example, we start at top left corner, we move further along and further along, and eventually we might end up down here. And this is sort of a nice example where we can sort of see problems of material shading and why sort of we were interested in WorkGraph. So if we take a closer look at this, we can sort of see all of our 4 threads. We can sort of draw a lifetime diagram for these, sort of examine what they do. When we said before, we'll map the 4 pixels of like the 2x2 area onto these threads. Like each thread calculates 1 pixel. And the problem here is, as I sort of mentioned before, is these materials might have different sort of computational complexities. So if, for example, just 1 pixel has the really expensive material, that will hold up all the other threads as well. And additionally, this is sort of running on SIMD hardware, so all the threads sort of need to execute the code in lockstep. So we can't actually run sort of different code in parallel on a GPU. And the actual execution timeline would look like this, sort of be serialized out one after the other. And this is often also called thread divergence, and this is sort of bad for performance. So what we would like to have is cases like this, where all the threads do the same work. We don't have any thread divergence. This is what we like, and the solution for this is WorkGraphs. So just a quick sort of speed run through what we've seen so far. In this sort of tutorial for material shading, sort of the baseline is that we have a, the baseline would be we're starting with sort of a compute shader that would render a scene. We have the sort of usual compute shader semantics here, which just declare, okay, in this case, we're not doing 2x2 threads. That would be a little bit small for GPUs. Instead, we do 64 pixels at a time in sort of 8x8 layout. In our tutorial, we just say we're doing some ray tracing that will give us a surface hit and a material to shade. And then further down below, we just say, okay, for each of the different materials, we have a switch case statement and just call the material shading function for each of the different materials, and that's where our thread divergence comes from. So obviously, as I said before, solution is work graph. What is missing from this picture? Obviously, it's sort of all the work graph semantics, so sort of back to the drawing board on these. Let's turn this into a work graph node. We'll start by the shader node declaration at the top, and we'll continue down further along. I said before that sort of work graph work is sort of launched by records, so let's grab one of those, which declare record struct. Then Bastian has already told you, like if you declare the record as like the input, we need to sort of pay special attention because all of these node input record types depend on sort of the launch mode of our node. We haven't set one, so let's discuss that one. Obviously, we want to have multiple thread groups, so we choose the broadcasting launch mode for this example. If you sort of look on your cheat sheet on the broadcasting launch mode section, you will find for broadcasting nodes, the input is declared as a dispatch node input record. And you'll also notice that we're missing some of our work graph attributes. For example, we still need to set the node dispatch grid. We can either set this sort of statically. For example, here would be 480 by 270 thread groups. If you're good at math in your head, you'll realize that with like 8 by 8 threads per thread group, this will cover a 4K image screen. But we're not always running at 4K, so let's make this sort of more adaptable to lower resolutions. We'll switch this up to the node max input dispatch grid. This will just say, okay, this is the maximum grid, and then obviously we still need this new SV dispatch grid semantic as part of a record. This will then set the actual dispatch grid, which will be used, and this will sort of be tied to our node whenever it's launched through sort of this dispatch, through this dispatch input record signature where we sort of receive the input record. So now we've turned this compute shader into a work graph node, but we're still sort of missing the most important part, which is the switch case statement, which is where all sort of the thread divergence came from. And this is still exactly the same. So basically, we've achieved nothing other than we're using work graphs now. So how can we sort of solve this? Well, one idea would be, okay, if we have all these different material shading functions, for example, sky, sphere, and plane, let's just sort of move them out to different nodes, because then if we sort of run these nodes, they would sort of run together, and we don't have the thread divergence anymore. So let's just do this at the example of the shade sky function. We'll declare a new node for this. We'll very creatively name it shade pixel underscore sky. From the name, you can sort of already imply, okay, this will just shade a single pixel instead of sort of processing the whole sort of 1080p or 4K image. And this will be for the sky node. As it's like a single pixel, we can use the thread launch mode before, because we just have one thread per pixel. That fits perfectly together. With the thread launch mode, we obviously need to set the input node type to sort of the thread node input record. This also then brings us onto the record that we're going to use. In this case, just call it a pixel record. And then there we'll pack everything that we sort of need to know for shading a single pixel. Obviously, we need to know where the pixel is to be able to write the output later on. We need to know the ray that we use to sort of hit whatever we have hit for this pixel. This will also give us some information for then how to shade. And then we also need to know the sort of distance the ray has traveled. Together with these, we can sort of reconstruct the three-dimensional position of the pixel in space. And with this shade, for example, the checkerboard pattern. Then, sort of in our node, we can read this input record. You can already also find this on your cheat sheet on the thread node launch. You can just use the get semantic. Then we have the pixel record, just as a local variable. With this, we can then sort of throw the ray into the shade sky function. That will still return sort of a four-dimensional color vector. And then we can use, in our tutorial, we'll use sort of the write pixel function. But here you could write it to a UAV or whatever to sort of output. And here, obviously, we use the pixel coordinates to sort of know where we write these to. All right, that's sort of the shade pixel function done for the sky material. Now it's sort of time to sort of rinse and repeat for all the other materials. Obviously in your scene you might have more than 3, in a tour it's just those 3 to save you some sort of typing work. And one nice thing is if we sort of declare the same for the sphere and plane, we can use the same pixel record for these as well, so we don't sort of also save some sort of work typing all of those record definitions out. Sort of now with all of these nodes defined, we need to be able to output records to them, so sort of back to our render scene node. To sort of get rid of this thread divergence switch case statement, we now want to sort of output a record for each of the pixels corresponding to the material that we found in it. But there's a problem. If we sort of would declare each of these materials, here you see the example for the shade pixel sky material, if you would do the same for the plane, the sphere, and many other materials, we'd soon hit the limit. We'd soon sort of hit the limit of the 256 records that WorkGraphs allows. And as you can see, this is a screenshot from a Nanite debug view. There are more than those 3 materials that we have in our simple example in a sort of real-world application. So how can we solve this problem? Well, WorkGraphs has a nice feature for us here, and that's called a node array. A node array basically allows you to combine multiple nodes of like the same launch type and same input record into one sort of larger meta node. And we can use this for all of our shade pixel nodes here. We can just combine them in a node array shade pixel. And if you're wondering what those sort of zeros that we already had when declaring the node ID were, that's sort of the index in this node array. So we set this to 0, for example, for the sky material, to 1 for the sphere, to 2 for the plane, and so on and so forth. And what that will do is we had our 3 different materials before. That'll sort of combine them into one larger shade pixel node array. And then the nice thing is if we go back to the sort of producer side of things, we don't actually have to declare each and every one of those lines. We can just declare, oh, we're outputting now to a node array. And so now we sort of can target each of those nodes in our node array with just a single output record declaration. Obviously, for the validation to still work, as we mentioned in the beginning, the validation sort of checks are all the connections there. The validation layer still needs to check are all the materials that we assume are in a node array actually there. We need to specify the size of the node array. In this case, it's 3. So the validation layer will check that sort of all the 3 materials are in this node array. But for example, you can also set this to just unbound or sparse nodes, and then the validation will just not check. And obviously, then you need to check before outputting a material record to it. Otherwise, you're sending a record to a node that doesn't exist, and this also results in sort of undefined behavior. So with this sort of declared, let's take a look at what changes we need to make when sort of sending a record. Here we're still sort of allocating 1 record per thread, so we're still using the thread node output record. That will sort of give us our small record box, which we can sort of store stuff into. But now we sort of need to select which of the materials we actually want to use, so which of the nodes in our node array to use, and we do this by this small sort of node array index here. In this case, we just use the material index from sort of the array hit that we got before. This is sort of the index that we had in our switch case statement, which is causing all the bad sort of thread divergence. And you can think of this will sort of determine the color of the record or the target of the record. Then writing to the record is still like the same as before. We can use sort of the .get intrinsic and then write stuff into the record. We sort of package everything together. Then we call output complete because we're done writing, and that will sort of send the record off to be processed by the WorkGraph system. And that record will then arrive at sort of the material that we set here with like the material index at the top. So just to summarize what we've done here, we've basically written a classify execute pattern where sort of the render scene will classify, okay, this is the material that I'm going to use for this pixel. And then we use all of the we moved all of the execution, all of the material shading into dedicated nodes and bundled all of this together with a node array. So in the beginning, we want to solve thread divergence with this, so let's take a look at how this would be executed in a GPU. So we again switch to sort of our cursor view of the input image with like less pixels because easier to visualize. Those pixels would then be processed by the render scene node, and this render scene node, as we've seen, sort of would more or less sort all of these pixels into the different material nodes. So all of the sky pixels would go to sky, all the sphere pixels would go to sphere, and so on and so forth. And by sort of sorting this, we can hopefully eliminate thread divergence. And to see this, we bring back our sort of small thread from before. Now we sort of don't actually, we can no longer sort of map all of these 4 threads to sort of individual pixels on screen, but we can map these threads to sort of records in sort of the input record queue, as you could call it, for like the node array images, for the node arrays. Bastian has already said that sort of the GPU will try to best use the thread groups available and combine multiple records into just a single thread group. And here we can combine, in our small example, 4 pixels for the shade sky into one thread group, or we can combine 4 pixels for the sphere in a thread group. Those will have a longer sort of wave lifetime because it's a more expensive material, but that doesn't really matter because we sort of have thread coherence between the materials, so they're not sort of holding up any threads that try to do something else. Same with the plane. And with this, we basically remove the thread divergence that we sort of tried to solve before. So you can see that with work graphs, we can increase the SIMD efficiency by removing thread divergence in a very easy way. And we can also see that node arrays are an essential part of this for being able to sort of cluster multiple nodes of different materials into this sort of larger node array. Now this is part of the work graph playground, one of the tutorials that you hopefully will do in your at home. We also have a sample available for this on GPU Open with like many more materials and sort of standalone sample that you can also then sort of use and if you want to see how you would set everything up for on the CPU side as well. So with this, we can move on to some 2 more concepts for advanced work graphs. One of them would be recursion. As we said in the beginning, if we sort of look at the structure of a graph, it has to be a directed acyclic graph. So connections like these that sort of loop back through multiple levels would not be allowed. However, there is sort of a small star with the acyclic, and there's that self-recursion, so where one node calls itself, is allowed. Obviously, that increases dramatically increases sort of what you can do with a work graph, because with this recursion, you also have the option to add amplification to it, because every time the node recurses, it cannot just send a single record, but for multiple records. And obviously, there are many applications for this. Bastian will talk a little bit about procedural generation later on, but you can also imagine that you could solve subdivision surface problems with this or some procedural fractals, and that's actually what we're going to look at next. One of those procedural fractals is part of the work graphs playground in the next tutorial, and that's the Koch snowflake. With the Koch snowflake, we basically start with an equilateral triangle at the start, and we sort of have a formula for taking one side of the triangle, so one line, and dividing it into 4 more line segments, and we can do this on and on again in a recursive way. So for example, here we would have a star, and if we refine it further and further, you can see we're slowly getting towards a snowflake. So how does all of this then look in sort of the HLSL code? Well, basically, we have our node here. The node ID for this would be the snowflake node. We're using thread launch mode here, so nothing really new here. And the sort of great thing with recursion is basically we're not adding any more concepts to it. We just declare a node output for the snowflake node using obviously the same record that you used at the input. So using the same ID here, but one sort of slightly new addition is that you need to specify how many times you expect your node to be recursing itself. So we'll get to why this is needed in a bit. But for example, in runtime code, you can then also check against this recursion limit with sort of the get remaining recursion levels. That will tell you, okay, how many more times can I recurse? And if this is 0, you can no longer output a record to the node itself. So why do we actually need this? Well, we said before that the longest chain of nodes in a work graph cannot exceed 32 nodes, and the node recursion actually counts towards it. So the node at the far right here would be at node depth 3, but if we introduce recursion, for example, to the node before it, it would be bumped sort of one level further down for just one recursion. If we do 2, it will get bumped further down, and so on and so forth. And as I mentioned before, this is also part of the work graph playground. So the snowflake is already inside the 4th tutorial for recursion, and your homework would be to draw the Menger-Sponge fractal, which is the one on the right. Basically, it's the same concept. You just take one block and divide it into 8 new blocks, which then sort of recursively call themselves. Right, with recursion out of the way, the sort of last advanced concept that we need before we can look at the procedural content is synchronization. So you can imagine, for example, if you're using work graphs to replace the traditional long chain of compute kernels. For example, if you have an image filtering pipeline, you're doing some blur filter, you do a horizontal, then a vertical pass. You can only start your vertical pass once all the sort of thread groups from the horizontal passes have finished. So obviously in work graphs, if we want to use work graphs for this, we need to have some way of expressing this synchronization. You can imagine you could, for example, do some atomic counting and stuff, but work graphs has a nice built-in way for this. So to look at this, imagine you have your node here, you get an input record. The input record tells you, okay, I need you to dispatch 2 times 2 thread groups, so 4 in total. The node at some point would start work at this. What does this look like? Well, we have our 4 thread groups here. They all sort of work away, computing, for example, passes of the blur filter. Then at some point, these thread groups would finish their work and sort of die off one by one until we have 1 thread group left. And what work graphs allows you to do is have sort of a programmatic way to say, okay, can I check if I'm the last thread group? And if you are the last thread group, you can sort of do a special action. For example, you can launch a record for the next pass in your image filtering chain. We again have a tutorial for this in the work graph playground. Here we're not doing image filtering, but instead we're sort of trying to capture this moving, whatever you call this, with a bounding box by sort of using different or multiple threads and multiple thread groups in a broadcasting node. So how does this look like in the code? Here we have lots of threads and lots of thread groups. We have 32 threads and 32 thread groups. And all of these threads are sort of drawing parts of this wavy figure that you saw before. And to compute the bounding box, obviously, we sort of would have to wait for all of these to finish, and they all sort of need to contribute to a shared bounding box. Let's start with sort of the first part. We can use sort of one new intrinsic on the input record, and that is called finish cross-group sharing. If sort of all the thread groups in your dispatch call that one, finish cross-group sharing will return true for the very last thread group to call it. And then you can sort of do some special action, in our case, drawing the bounding box afterwards. As this is an action on the input record, there is a small change we need to do to the input record, because this sort of needs some sort of data to be able to track how many thread groups are still alive. And for this, we sort of need to annotate the input record with this node track read-write input sharing declaration. So you don't actually have to do anything of this atomic counting, whatever. This is all done for you by the work graph runtime. All you need to do is add this small bit of code. As this sort of implies this is a read and write operation on the input record, So instead of declaring the input record with a dispatch node input record, we now need to declare it as a read and write dispatch node input record. This is the advantage that we can now also write to our input record, and the input record is shared across all the thread groups of our dispatch. So we can use this to do fun stuff like, for example, computing a bounding box with atomic operations. So basically the input record gives us a small piece of shared memory that all the thread groups in our dispatch have access to. And in this case, we just do an atomic max and forward down an atomic min operation to compute the bounding box. Obviously, with these atomics, stuff in flight and caches might be an issue. So you still need to sort of have some form of barrier. In this case, in HLSL with work graphs, there's a new barrier intrinsic, which gives you greater control over what you're actually going to barrier. In this case, we just say, okay, we want to have a barrier on the node input memory. If those atomics are sort of done, we want to have sort of the final result read back available to us. And with this, we can then sort of use the ABB min and max that we've computed with the atomic operations further down below in the very last thread group to draw the rectangle around our sort of dancing figure here. So hopefully you've seen with this that with work graphs, there are sort of many more advanced concepts. You've seen that node arrays, for example, can be used to implement a classify execute pattern and remove any thread divergence. You've seen that we can have recursion in our work graphs, which gives you greater flexibility and a lot more options for what you can do with your work graph. And if you're running with sort of longer execution chains, there is also some basic synchronization available in a work graph to be able to implement that as well. And with this, I'll hand it over to Bastian, who is now going to tell you how you can use all of these concepts to implement many different procedural effects.
All right, I will show you some examples of procedure generation that we could do thanks to work graphs. And this is based on 4 examples that we did. So we did these examples and we published 2 papers with them, and some other things. For some other things, we published some blog posts on GPU Open if you're interested into more detail. All right, procedure generation is often done for modeling purposes, and I want to show some software. So here this is Houdini, and it's very famous for its procedure generation. Second software that you probably all know is Blender with its geometry nodes. And a recent competitor is Unreal Engine itself. So inside the engine, there's also now a procedural generation system. And what all these 3 have in common, they are all based on node graphs. And these nodes are connected, sending some data and by an artist, and these nodes are reusable. So that's where basically the motivation comes for maybe work graphs could play a role. Another thing I want to look at here is where these softwares generated procedural geometry and where it's used then. So for Houdini and Blender, if you care about real-time rendering, the procedure generation for the most part probably happens on the CPU, and then it's exported to some polygon format to disk, and then for rendering in a game engine it's loaded again, then uploaded to GPU and displayed. For Unreal Engine, if the procedure generation happens in engine, you could basically skip this baking process and directly upload the generated geometry to the GPU, but generation still kind of happens on CPU. And what we want to do right now is to skip the CPU part and also generate everything on the GPU, possibly even on the very frame that we want to display the procedure geometry. Right, another thing I want to talk about is how procedure geometry usually is controlled, and this is something we call control parameters. So you can see this muffin, the shape of it is described by 3 values. You could go more complex than that. So here we have a bounding box, and you could say, okay, this bounding box defines the shape of this bench. And if an artist drags around this bench, when he's, for example, modeling a scene, you could adjust the shape of this bench based on this bounding box. And this is all based on procedural rules, and generating this every frame is quite very useful for the artist because it's helping him being productive. And you could go more complex than a bounding box. For example, how about a polygon defining a whole building that is generated when required. And for the first example, I want to talk about our market generation. And for this, we went on a research trip to the Coburg Christmas market. And we did an analysis of its shape and noticed, okay, this shape could also be described as a polygon in 2D. And from the corners of this polygon, there's like paths to the center, all right? And then there's some intersecting paths, and in between these paths, there's something we call booths islands. So here would be like some booths, and here we would like to place some fitting assets like a tent or tables or whatnot. And then the center of our market is like a special area, usually with some fitting prop like a statue or a tree or a well. And when you look at this shape, it's very similar to something called the straight skeleton of a polygon. It's very common in procedure generation for generating roofs, but we will use it for this market. And how would you generate the straight skeleton? So you shrink the polygon parallel to its edges, and until one of two events happen. So one event is the merge event, when two vertices of the polygon merge into one, and and the other event is when the two polygons split into two. All right, so how does this work for a marketplace, and how would we implement this in a work graph? So if you have a node called market and receives this polygon as input. This is how this looks like in code. So we have a node market and receives a market record, and this market record is just this polygon. And we launched this node in broadcasting launch mode with a static grid of one group. And this group has the number of market points as the number of threads. And what we do now, we can parallelize a little bit. We can say, okay, each thread gets 1 point of the polygon, and we have to find the next event of the straight skeleton to figure out whether we can generate something or not. That's what we do. So we use each thread gets 1 point and calculates when its next event will happen. And then you have to synchronize the threads, for example, using wave intrinsics. So the closest event is then the wave active min of all the event distances. And let's say in this case, it's thread 2 would have the next event. So we still have some space. So let's create our first ring of market booths. So let's shrink the polygon. This also happens in a way that each thread changes its own point. And now we have some space for paths. So let's write some output records to a node called path. And let's make some space for the paths. And let's also write some output records for a booth island. Now, these nodes should draw fitting assets into their area. For example, in this case, a booth island is just a record with a quad, and it should draw some assets into the area given. So how do we output geometry? So one simple way to do that has existed for a long time is execute indirect, and for this we write to a draw list. So here we would need some kind of like reserve a slot in memory in the draw list using interlocked add, and then we write to that reserved slot. Another thing you could do alternatively, if you want to do ray tracing, you could write that instance, for example, of a tent into a BVH instant list, and then after the work graph has finished, you could build a BVH and then use that for ray tracing. And well, these two you could do, but they are using execute indirect basically, and that's very sad because we now have work graphs. So you could obviously also just directly draw the geometry using mesh nodes. All right, so back to our market. We have now established how we output geometry from our work graph. and can now continue with our market generation by just recursing, right? We can, with workers, we can recurse, and now we have again a polygon, so we can just recurse the market and generate the next layer of booth islands. And again, write records. All right, and now we have arrived at our first event. It's a split event, and now the market splits into two. And what we can do now, we can recurse into two markets, right, with work graphs. And that's exactly what we do. And one half is now finished, and we finish with the special center, maybe a well. And the other market still has some outputs to do, and will be done now, and it finishes with a tree. All right, this concludes the market generation. And here you can see this in action. You also earlier saw it with the live demo. So here we take around a control point of the polygon, and you can see the generation updating instantly. And for this, we need like 1 millisecond, although this is barely the generation time, it's other things. And you can see 630 instances generated. One more thing that I didn't mention, you can see here in the red bounding box, are these garlands. And these garlands span in between two distinct booth islands. So they were generated independently from each other. So how do we achieve this? And here's this very similar thing from Unreal Engine PCG. So here we have a control structure, this island in the center of the trees. And you see these two white bounding boxes. And when the user drags it around and lets go of the dragging, in the red box, you can see a structure generate, basically a bridge to this island. So when the white box intersects with something, this structure is generated. And it doesn't intersect with anything, it's not generated. This is something we call dependent generation. So for example, for the blue box, you don't see anything generated. So dependent generation, how do we do it? So here you have this example that I mentioned. You have two tents, and we would like to draw a garland if possible. So we have these points, how to find them. So we need some kind of spatial GPU data structure that is fast to create and update and to access. Any ideas? Ray tracing BVH. Well, I mentioned that we already have that. We can write to a ray tracing BVH, so why not use it? It's just a matter of API calls, right? Accessing it and building it. So why not make things simple? All right, so what we do is we add to our BVH, we add these markers, these red boxes. They are not used for rendering, so we use these instance flags in BVHs, so we hide them when rendering. And then each box shoots rays into its vicinity, and then if it finds another marker, our garland is generated. Right, another thing you can do with dependent generation is ivy generation, as I will demonstrate. So here's our goal. We have existing geometry and want to generate ivy on top of it. So what we do here, we have a node called the ivy branch. And as a control structure or control parameter, it receives a transformation. And this is the starting point where the ivy should start growing from. Okay, now you have some object we want to grow on. And this is basically the loop the ivy node does. So the first thing it does, it shoots rays into the growth direction and finds a surface to grow on. And then according to the result of these rays, we update the transformation. We draw some assets, output some assets, for example, a branch and some leaves. And then there's a random chance that our work graph or our node or ivy splits into two, so to simulate branching. So now we have two. All right, and then we recurse. And this way we can grow ivy along a surface. And here you can see this in action. We have this starting point, and if it doesn't find anything to grow on, it just grows downwards, like gravity. And yeah, as you can see, the artist drags around this point, and the generation updates instantly. Now, we want to generate a lot more ivy, so let's just add a parent to our ivy branch, the ivy area, and it receives a bounding box as input. And inside this bounding box, we would like to start ivy branches to grow from. All right, so the Ivy area, all it does, it also finds starting positions using ray tracing to start Ivy branches, and then it does outputs to the Ivy branch, which then grows the Ivy by recursing. This is how it looks in action. So here you can see us dragging around this bounding box, and you can see the whole roof being filled by Ivy in real time. Another thing that you will see in the video very, very soon is that this building is actually also procedure generated, and you can see that it works with each other. And if you want to play around with the system, we have an official sample from AMD on GPU Open and GitHub, so go check it out. All right, so this is the GDC demo from last year, and let's talk about timings. So for generation, we need about 3 milliseconds to augment the scene, depending on the camera position, right? When we, for example, only look at the market, we don't generate a lot of, like we can cull a lot of Ivy generation because it's not visible, so we're a little faster here. And we also can see that we generate a lot less, but the render timings are absolutely horrible, especially for this low polygonal scenes. And the reason for this is that the number of draw calls is very high, right? We write to an instance list, and well, one object is one instance, so we have like almost 80,000 draw calls for the overview scene. So how could we fix this? And here's how we use the coalescing mode in a somewhat unusual way. We want to combine draw calls to the same assets using instancing. And what we do here, we have a coalescing launch mode, and it receives up to 256 draw asset records, and it outputs up to 256 draw asset records, but in the best case, only one, right? If you draw of all these 256 records are to the same assets, it just output one that combines all of these. So what the node does, it has like possible outputs and then sorts, okay, all the branches get one output, all the tents get one output, all the leaves get one output, and so on. And this worked surprisingly well, as you can see here. So from 80,000 draw calls, we went down to 1,000 approximately, and the render times reduced significantly. So this is a weird way of using the coalescing launch mode, but it works super well in this use case. And also the generation timings went down a little bit. All right, so this was the GDC demo from last year. Let's talk about this year, procedural foliage generation, so the grass and the trees. So for the generation, we wanted to do 3 things. We only want to generate the vegetation that is within the frustum, of, for example, the camera and the shadow camera that points towards the camera. So we only wanted to generate front-facing triangles and not back-facing triangles. And we wanted to have level of detail. That was very important to us. So this is part of the same frame that you can see in the top, but it's like very far away from the camera, and you can see like it's very low poly. All right, for the grass, we have the camera frustum here. And we need to basically launch enough threads to fill all the ground with the ground clutter that's within the frustum. And for this, we have a node for all the parts of the scene. It gets launched for all the parts of the scene that should receive clutter grid or should receive clutter. And we now want to launch individual tiles for generating the ground clutter. And for this, we need to find like the grid to launch. And we basically find the axis-aligned bounding box of the frustum in world space, and then have an offset value and the size of this grid. That's part of the dynamic broadcasting launch dispatch grid, and then we launch a grid of clutter tile kernels. So this is the record, how it would look like. All right, and then within this frustum, each individual thread group of clutter tile can tell whether it's inside the frustum, so it's like a detailed culling, and then it can output to different nodes based on some information in the world. For example, if there's nothing special and there's some sun, then we generate a grass patch. If there's little sun, then we generate some mushrooms. These are all individual mesh shaders, by the way. Or if there's like a flower, then we generate some bees, and this is also an individual mesh shader for a bee swarm. Right, and this way we can fill only the frustum with, with ground clutter. For the tree generation, it's a little bit more complicated. So I said that we wanted to generate only the parts that are front-facing, so we wanted to avoid generating back-facing triangles. And for the tree stem, we did an analysis on which part of a tree stem points towards the camera, and we derived this formula down here. It's basically based on the radius derivative and the camera angle. And with this, we can see an example here. So we have here two camera views. One on the right is static, one on the left is rotating around the camera and is defining the procedure generation. As you can see, we only generate the parts of the tree that point towards the camera. And here in pink, you will see that, basically on the right side now, you can see that basically half of the tree is missing. All right. Next up, we wanted to have a dynamic level of detail for the tree stems, and here we use tessellation. Pretty straightforward, but we implemented it in a mesh shader because we wanted to use mesh nodes. And here you can see our tessellation factors. We have 3 of them. Basically, and the user can say, okay, per pixel, I want to have this many triangles. And here you can see this in action. So on the right side, again, a static camera. On the left side, we move away, and this defines the level of detail. And here you can see the number of, or the triangles disappearing. And when a branch is too thin, for example, thinner than a pixel or so, we just discard drawing it. And this is all dynamic decisions happening in one work graph. Now, as we reapproach the tree, you can see the triangles appear again. And we are back at like 350,000 triangles. For the leaf generation, we do something similar. So for the leaf level of detail, we use an old trick that is that we generate, when we are far away, less leaves, but compensate by just scaling them up. And this way, on the left side, you can see the tree looks almost the same, but on the right side, you can see there's actually a lot less leaves that are just bigger. And all of this is also happening in the work graphs, and a dynamic decision in the work graph, oh wait, the tree is pretty far away that I'm generating right now. Let's do this dynamically, and also you can see that it's all continuous, so the leaves just don't disappear. The leaves that should disappear just shrink slowly, so the user doesn't see any popping. All right, another thing you can do with real-time each frame procedure generation is just change the rules a little bit based on wind speed and the current timestamp, and this way you can achieve pretty decent animation, I would say. So you can see our animation based on different wind speeds, from a breeze to a pretty decent storm on the bottom right. And another thing you can do is you can have the generation adjust to environmental factors. So for example, here you can have just a floating point value defining the current season. And as we approach winter, you can see the leaves of our trees getting red and brownish, and then slowly falling off. And maybe now we are in winter, we have some snow on the branches. Oh, it's getting spring, so there's some blossoms growing. And in just a moment, you will see that some of the blossoms will turn into fruits that slowly grow. And all of this is just based on this one floating point value, and then the work graph crunches it to this geometry. And there we go, and you can see some apples growing. All right, another thing we also wanted to have is real-time editing, right? And as you can see, we added this patch of apple trees in real time, because generation just is based, happens every frame, it's just based on a small set of parameters. And as the generation is based on a random seed, you can just change it on the fly, obviously, and there's 32 bits worth of trees, apple trees that you can generate. All right, another thing we did is, because we have continuous level of detail, right, so we can change the level of detail without any discrete steps, we can have a dynamic level of detail. So we can say, okay, the last frame took a little longer than we would like to, maybe just crank down the level of detail just a little bit for the next frame to like hit our frame target. And here you can see this in action, how we can reduce the number of triangles quite significantly by just changing this level of detail factor. And you can see the result of this. So here is our benchmark, and we can see the performance, like we fly through our test scene, and the performance varies quite a lot because like the generation also has to like generate different number of triangles for different parts of the scene. And with our automatic dynamic level of detail, you can see we hit our frame target of, in this case, 120 Hertz very nicely. All right, these were all 4 generation examples that I wanted to present. You can later, because we brought this PC here, you can come up here and play with the demo if you want to, or you can download our official sample, which is a subset of it. All right?
All right. So as a sort of very last point on our agenda, we want to explore how GPU work graphs actually work under the hood. Yeah, that's working. Obviously, I can't tell you all the sort of top secret details on how we implemented this on our GPUs, but I want to do with this section is sort of give you an overview of some ideas on how this might be implemented, and most importantly, some of the challenges that come along with sort of all the GPU doing its own decision making, and so on and so forth. So before we sort of can discuss how work graphs work, let's quickly remind ourselves how anything or any work on a GPU works. So what you might have in your code is something like this. You have a dispatch written to a command list. For example, you're dispatching a compute shader. And to actually then execute this compute shader, you need to submit this command list via the sort of execute command list command on a selected command queue. What that will actually do is it will basically take your command list that you recorded before, it will move it down to GPU visible memory, and then on our GPU, we basically have a ring buffer, which the CPU uses to communicate with the GPU, and in there, in this ring buffer, we sort of encode, hey, I have this command list, maybe take a look at it and do the work. On the GPU, we have a sort of hardware component, which is then sort of tasked with running this. We call this the command processor, or CP in short. The command processor is sort of split up into different parts. At the top, there's sort of the micro engine scheduler, or MES for short. That will just take care of some sort of housekeeping and sort of manages the different command queues and how they're connected to the command queues that you as a programmer are seeing. Then to actually do some work, the CP has access to different actual command queues. These are all sort of separate hardware blocks. And these are sort of classified into some graphics blocks and some compute blocks. If you're using DirectX, you'll already be familiar that there is a graphics queue and a compute queue. Those are what those then match to. In our case, let's just say we submitted this work to a compute queue. So the micro engine scheduler, in this case, will pick compute queue 0. There's another ring buffer attached between those two and sort of propagate downwards this command that is downloaded. Hey, here's a command list, do some work. This compute queue 0 is then sort of programmed by some firmware. Don't worry, we actually don't ship firmware on floppy disks. That's part of the driver that you install on your system. In this firmware, we then sort of have programmed, okay, if we get this execute command list command, go into this GPU visible memory, go fetch whatever is in there. In there, there'll be the dispatch that we had earlier, and then this compute queue can sort of launch or get the SIMDs to work away on this large compute dispatch. So we've seen that we can just sort of put some commands into memory. Those will then get executed and by sort of our GPU. So if we want to launch work from the GPU, why don't we just write something from the GPU cores, like the SIMDs themselves, into this memory, and then if we write of the right format, the GPU should execute that. Well, that's actually the first step on how work graphs work, but we can't just write a command list. With work graphs, we sort of have a very dynamic workload where you sort of read and write at the same time. So instead of a list, let's say, okay, we're using a ring buffer. In this ring buffer, we can then not store sort of individual dispatch commands, but for example, we can store our records. And as we have sort of multiple different nodes in our work graphs, let's just grab one of those ring buffers and just assign it to each of these nodes. Then we can go back to sort of our firmware, and we can adjust it a little bit, such that it will continuously check all of these ring buffers. If it will find some work available, it will launch it. Pretty simple, right? So let's take a look at some example. Let's just say there is a record sitting in the ring buffer for the node A in this case. In here, we'll find a record with a dynamic dispatch grid of just 2 thread groups. So compute Q0 will see, oh, there's a record available. It will sort of look at the record, see, okay, I need to launch 2 thread groups. So it will do that. And those 2 thread groups will then sort of work away. For example, they will all generate some outputs. They're sort of denoted with the small boxes inside the SIMD blocks. Those outputs should go into the ring buffers for node B and C. So at the end, the node will sort of copy these records into these ring buffers. Obviously, then here it's just the first SIMD. Then the second SIMD will copy its data into it. Obviously, they will sort of then be available to the compute queue or the work graph system for execution. And as we sort of have consumed this input record, of which these sort of 2 thread groups were launched, we can clear it from the ring buffer of node A. So then it's sort of rinse and repeat. The compute queue again looks at these ring buffers. This time there's some work available for node B and node C. So we can launch this to basically now the whole GPU. Let's just say we have sort of 1 thread. We just require a single thread group for each of these records this time. And all of these thread groups then again want to produce some output records. This time they both want to write to node D, so into the ring buffer of node D, and we have many, many records waiting to be written. So we can sort of rinse and repeat again. We write the first record, second SIMD writes its record. It has this time 2 records. The third one just has a single record. The fourth one has 2 records again. Then we move on to the fifth, 2 records again, and we run into a problem. Because now we don't have any more space in a ring buffer for node D, which is bad. That shouldn't really happen. But we have a second problem, and that's that the entire GPU is sort of busy with the node that we launched for nodes B and C. So we also don't have any available compute resources to get rid of some of the stuff that's already sitting in node D. So basically, we've arrived at a deadlock. And that's where sort of the complexity of work graph comes in, because the GPU only has like a limited memory available to sort of partition through these ring buffers or in any sort of memory management scheme. And with this limited memory, it has to sort of be able to execute any work graph that you throw at it. And for this, we have sort of a term that we call forward progress. So if we go back a few steps to the situation where, let's just say we believe things went wrong. And that's the step when we had the items sitting and waiting in ring buffer for node B and C. We just executed them all without sort of ever looking if we can fit all them in the ring buffer of node D. Because if you remember back when we sort of talked about the concepts of records, we said that we need to have this max records sort of annotation for each of the node outputs, telling the work graph runtime how many records each thread group will produce. So what we can do is, whenever we want to launch, for example here, a thread group for node B, we can use this information that each of these thread groups might produce 2 records for node D, we can already reserve some space in this ring buffer. By reserving this space sort of early on, we'll make sure that we never run out of space for the ring buffer of node D. So if we continue this for more of the nodes for node B, we can see, okay, there's another 2 reservations, another 2, and then the final 2 reservations. And we can see that this time we cannot actually launch any work for node C because we don't have any space for the reservations in the ring buffer for node D anymore. This obviously limits the occupancy a bit. One solution might be just change the size of ring buffer or move to a more dynamic allocation scheme. But in general, we need to find we still need this way of guaranteeing that whenever we launch a node, it's able to finish and write all of its output without causing a deadlock. That's sort of the huge complexity of work graphs. Yeah, and sort of the one thing that we as the implementers of this need to figure out to enable all the fancy things that Bastian just showed to just work. Obviously, one thing that Bastian showed were the mesh nodes. So how do those then work? Well, as we said before, sort of mesh nodes, they're basically just a mesh shader. They behave similar to like a combination of mesh shaders and broadcasting shaders. They have some output that this time feeds not to other nodes, but directly to the rasterizer, and in there we can put a small mesh. So before on a GPU, we said we have these sort of compute queues that we used for work graphs so far. Those can take care of, for example, all the compute shaders, like the irregular broadcasting, thread, and coalescing node launches. But if we want to draw stuff, draws need to be sort of handled by one of the graphics queues. That's just sort of one limitation that we have here. So we need to assign all of the mesh nodes to one of those graphics queues. Luckily for us, the graphics queues are more or less similar to the compute queues, so they're also programmed by firmware, so we can sort of use the same logic for scanning all the ring buffers looking for work. But now we sort of have 2 queues running at the same time, one just dealing with the compute nodes, one dealing with the graphics nodes. So when sort of dispatching this command list, we need to use something that we call a gang submit, basically like a handshake between these 2 queues. They say, okay, let's just team up on this work graph. We work together. Compute queue takes over all the compute queues. It has to do all this sort of complex forward progress checking that I've just explained before. And then the graphics queue has the simple task of just drawing pretty pictures on the screen. And with this, you can see if we have some records available for a mesh node, the graphics queue can, for example, just schedule the mesh node, and that will eventually then also trigger some pixel shader waves. And in the meantime, the compute queue can also schedule some compute work. And this way, sort of the GPU can feed itself more and more work and try to optimally use all of the available compute and graphics resources, maximizing sort of the occupancy completely automatically without you as a programmer more or less ever having to do anything to achieve this. So in summary, what we've seen is that, yeah, these work graphs are fully GPU-driven producer-consumer networks. They run entirely on the GPU. They basically offer GPU-managed memory, because if you think about it, the record is just a bit of memory that the GPU then takes care of, moving it from one node to the other and further down the graph. And with this, we also get the sort of very important part of our progress, because this GPU-managed memory is just comes from a very limited pool, so the GPU needs to manage this memory very carefully without generating any deadlocks. So hopefully now you've seen some of the complexities that come along with implementing work graphs as a sort of GPU hardware vendor. And with this, I think we can sort of conclude the talk with a little bit, our work graph course with a little bit of summary. And for this, I'm going to hand it over to Quirin.
Okay, thank you, Max. So I would like to conclude the work graph course here. and summarize everything that we have seen today and remind you what you have learned. What we've seen here, let me grab the laser pointer here real quick. So with work graphs, we can actually model data flow through a directed acyclic graph with trivial self-recursion cycles. And the interesting thing here is that the data flow is represented by records that you send around nodes. So what we have observed when teaching work graphs is that there's a common misperception that records are dispatches. That's not the case. Records are not dispatches, but they eventually trigger dispatches. This is something that I've seen many people having problems with. So records trigger dispatches. They aren't dispatches directly. So the specifics of these dispatches are specified by one of the three launch modes that you have over here. So we have the thread launch mode, we have the broadcasting launch mode, and we have the coalescing launch mode. So eventually with that you can combine all these concepts, and we've seen how we can do producer-consumer networks, and we've seen these examples from the tree generation demo, but also from the GDC demo that we showed in 24. And that actually enabled doing a lot of stuff on the GPU, actually doing everything on the GPU. So, and the memory for those records is automatically managed by the work graph subsystem, so you don't have to worry about it. Everything should run fully transparent to you. And it's actually nice that you don't have to worry about deadlocks and other types of things that you would probably be more concerned about if you would program it more directly. Right, so, and we've wrapped all these concepts into hopefully easy enough tutorials that you can maybe do on the way back. If you have a Windows computer or at home, it shouldn't take too much time. So there's a bunch of tutorials here, and we have like a final tutorial for you, which is called Recursive Grids, which combines everything. And then for those who want to dig deeper into mesh nodes, we have a very nice mesh nodes tutorial where you learn how to use mesh shaders and everything that comes with it. Everything is well documented in the comments, and we have accompanying markdown files with links and all the background information that you need. Yeah, so personally I found the records tutorial the most challenging, but once you have gotten over it, everything gets easier in my personal opinion. So, right, so this is what I've just talked about. So what we've also done is, you've seen these beautiful trees Max and Bastian have shown in High Performance Graphics and at Game Developer Conference. It actually fits nicely into a work graph playground tutorial. So you can download this from Bastian's GitHub site. There will be, if you download the course notes from Digital Library, you'll find the links. And you can just simply open it, it will compile a little bit, and then you have some handles here which you can control the tree. Actually very nice, and everything runs basically in the playground in HLSL code with work graphs. So what we also have is we have standalone samples on GPU Open. So we have a little compute rasterizer over here, and we have also some procedural generation stuff with mesh nodes going on, also available on GPU Open and on GitHub, and some blog posts on GPU Open. So there's a lot of more information going on here. And what we would really like to do is connect with you. So if you have any questions or get stuck somewhere or find something annoying or how we can improve the work graph playground, just get in touch with us. Just simply scan this little link over here and get connected. So this basically concludes it, and before I would like to go into the Q&A round, and we have some time for the Q&A round, I'd like to thank those people here, my team from Coburg University, and of course the team at AMD and Matthäus. So with that, I would like to open up the Q&A round. Oh, yeah, thank you.
Can quickly go back to the QR code
Hello.
if you have.
The question is more about planning on the GPU you were showing at the end. So for recursive nodes, I'm guessing you have unique nodes on the ring buffers to make sure they're not going to self-deadlock. And an addition question on that topic about, is there any cache coherence issues you've seen with loads that were executed in parallel? Because you were saying at the start of the presentation that it was maybe not contiguous in terms of order for dispatch sometimes.
Okay. So if I got that right, your first question was for the sort of ring buffers that I showed, the idea is how to implement this, how this would connect with recursion. As I said, this is just an idea for how you could implement work graphs. Basically, if you have recursive nodes, when sort of launching a record from the ring buffer, you would need to either allocate or make this reservation to the same ring buffer, or just sort of more or less unroll the recursion into multiple ring buffers. Yeah, that's sort of your two options. And then your second question, I think...
More about coalescing loads. So you said it was not guaranteed to be dispatched needed the full amount, or so did you see an impact on cache coherence on GPU?
Not sure if I'm getting your question right. So for coalescing, you mean the non-deterministic part, yes. The non-deterministic nature of it. That might, in theory, sort of, yeah, reduce your cache coherency. But basically, if you think about the ring buffers again and how a coalescing node would be implemented there, a coalescing node is just takes out not just one record, but a bunch of records of the ring buffer. So those would be in sort of consecutive memory again. So those could be consumed by just a few consecutive cache lines. So the ordering more or less, like the non-deterministic and the ordering guarantee, the non-deterministic ordering for it doesn't come from how we sort of read out of the ring buffers, but more or less from the order that stuff gets put in those ring buffers. Does that answer your question? Okay.
Hi, thank you for the talk. I have a question about the timings for the procedural generation. So it was around, I think, 3 milliseconds. On what hardware is it running?
That was on a AMD Radeon 7900 XTX.
Okay, and is it running each frame?
Yeah.
Yes.
Yeah.
We basically start with a blank slate.
Yeah. How would you break down this cost? Is it, because it seems significant, especially if you are targeting a high frame rate. So I was wondering if there are opportunities to reduce this cost in your sample, or what's taking the most time?
So the numbers are only the generation. So we isolated. I mean, except for the mesh. Like so for the low polyscenes you've seen, we generate the numbers are for generating the draw list. So the drawing is not part of it. So the 3 milliseconds you mentioned or we mentioned is only the generation. For the trees, it gets more tricky because you cannot really isolate drawing and generation because most of, like, big parts of the generation happens in the mesh shader, right, where we generate the actual triangles. Yeah, so...
But I mean, in the generation code itself, what's taking the most time? Is it anything you could, like, optimize or...
There is some longer sort of chains of nodes. And as we, for example, with the market, if you think back to what Bastian explained, it's more or less these recursively sort of subdividing or refining the market. As we just generate one market, obviously there isn't a lot of opportunity to run anything in parallel there because you can only generate the next ring of the market once the previous one is finished. So due to sort of this nature of the application, there is a lot of long-running ways with low occupancy. So the guess is sort of if you wouldn't just generate one market but 1,000, you would get the same 3 milliseconds. So that's sort of, yeah. For the demo, you could say, yeah, that's hindering performance. As a long-term thing, you could put more and more work in the same work graph, and then a GPU could pick more and other stuff. For example, if you already have some, let's say you've already run that part, you need to do some denoising or upscaling or whatever, you could fill the sort of gaps in occupancy on the GPU with other work. Okay. But we haven't done this for the demo. The demo just generates the scene and does only that in the work graph.
Actually, we have Max for the Ivy generation, following on up on that. So for the Ivy, I said we recurse like after every step. That's undercomplicated. Like we actually do 4 steps and then we only do the relaunch. This way we have like a trade-off of the like, we trade the launch overhead over, yeah, like basically how much we do in a wave, how long a wave runs. So that you have to like play around with that a little bit to tweak performance.
Okay, thank you.
In the materials example that you gave before, it looked like it relied on knowing ahead of time the shader paths the materials might take, but what different materials you have and how many materials you have. How do you think that might work with systems where materials are generated, material shaders are generated at runtime from arbitrary material graphs? Do you think you'd have to recompile the work graph every time a new material is added, and would that add significant overhead to bringing in new materials?
Yeah. There is a nice feature about work graphs, and that is that you can actually add nodes to a work graph after the fact. So for your use case, or for the use case for material shading, you could just, if you, for example, doing rendering, I mean, you would have to check on the CPU what materials are possible, but that holds true if you're using, for example, execute indirect for material shading. But if you encounter new material, you could just append this to the already existing work graph. I quickly mentioned, for example, when you need to specify the node array size, it also supports unbounded node arrays and sparse node arrays. Okay. So you can just tell the runtime, okay, I'm filling this node array as we go along. Don't validate it yet. And then in the shader, you can, for example, check if a specific slot in this node array is valid at runtime, and then output the material to it.
Cool, makes sense. Thank you.
Hi, thanks for the talk. A couple questions. Obviously, there's a lot of additional flexibility over like traditional compute shaders here, and a lot of opportunities for optimization, like you mentioned at the beginning. I'm wondering, what is the general overhead? Like, say I took a workload that worked well on compute shaders and used work graphs for that. How much extra overhead would I expect from using work graphs, from having the scheduler doing all of this stuff on the fly?
If you just have your one node, more or less just imagine the beginning of the materials where I just ported the compute shader over to a work graph. There the overhead would be relatively minor because most of the work graph stuff is more or less asleep because you're not really building a graph yet. But in general, if you have very simple problems, you're using a lot of complex machinery, like all the ring buffers, the forward progress checking, and those can add some significant overhead. For example, even if your compute shader waves have very short wave lifetime, the sort of amount of checks that need to happen in order for the work graph system to launch those, they can sort of outweigh the sort of wave lifetimes. So that's sort of one, obviously that's for us a great challenge to optimize this in the future. But for now, it's sort of, you sort of need to be aware of this latency overhead and sort of choose your work graphs that you want to port to work graphs accordingly. That's sort of the recommendation I'd give.
Thanks. Along those lines, I have a second question. Like, what do compilation times look like for a work graph? Is this comparable to, doing a similar workload in compute shaders?
Yeah.
Okay.
Basically, all the nodes just compile as compute shaders with a bit of overhead. You're compiling them all in just one call now instead of each individual compute shader. It's just one. In D312, it's called the create state object call. But yeah.
All right, thank you.
Comment on that, the playground only compiles this slow because we have print and it's kind of funky. It's not really, doesn't really exist in HLS, so that takes a long time.
All right. As I see it, we don't have any further questions. We still have some time, so either we can let you go a bit. Oh, you have one more question.
Yeah, I have one more. So back to the node arrays. Again, you said it was a gross explanation for the ring buffers, but does the node array itself having an impact on that scheduling itself? Does it limit the number of variants you can have if you have, as you said, sparse or very large numbers of arrays? Would it limit the number of variants that you can run before you have to start them?
Mm-hmm. So if you would sort of implement the node arrays with the ring buffers as I showed them here, they obviously would pose a challenge because you would need different ring buffers for the different actual nodes, but your reservations would be in a whole nother ring buffer because up front when launching you don't actually know what the shader is going to do. There's ways to get around this, but yeah, I think that's what I can say to this. But yeah, node arrays are challenging in some parts because you don't know what the shader is going to do.
Hello. Yeah, if we have a bit of time, would you mind giving a bit of a short overview of how you switch the PSO for the mesh nodes?
Mm-hmm. So basically, for mesh nodes, the nice thing is you have full PSO switching on the GPU. So not only just for compute, you're just basically changing the shader. For mesh nodes, obviously also changing the whole state. For example, you can have a mesh node with backface culling, one without. And what the work graph, sort of the compiler or or driver will do, it will try to find the most common state across all your mesh nodes and then only change the parts which change between different mesh nodes. So if, for example, all your mesh nodes use backface culling, we don't need to change that between switching PSOs. But the actual switching PSOs is more or less the same as if you would switch PSOs by just like the usual D312 APIs. Does that answer the question?
Yeah, and I guess you just said it from the mesh node. You declare it as a property. You're saying this is the PSO label that I want to use, or I don't know. Maybe this is a silly question, but I'm trying to understand. Like, if you have one PSO for your whole work graph, or you have like a set of PSOs.
Okay. So for work graphs, as I mentioned, sort of in the nodes concept, the compilation model is no longer you compile one sort of vertex shader, one mesh shader. You compile them into these libraries, and these libraries then obviously can get combined into the whole work graph. So they no longer use like the PSO terminology, but they're using in D312, it's called a program. So you set the whole program, and the program will then contain all the different compute shaders, all the different mesh shaders, and that whole program basically gets loaded onto the GPU, and then the command processor, whenever it finds some work, for example, for a different mesh node or different compute node, that will then look into this program, find the right shader, set up all the registers on the GPU that need to be set to more or less carry out a PSO switch, and then run the shader that way. So more or less you have a second PSO state shadowed inside this whole sort of program.
Okay, it's very, very similar to the XR in a way.
Mm-hmm.
Yeah, thanks.
Yeah, it uses like, if you know DXR, you're using the same create state object stuff. Yeah. All right, if that's all the questions, we can either let you go a few minutes early, or if anyone wants to try the procedural tree demo, we have, or the other demo wants to play around with it, we still have those available here as well. If nobody wants, we're still around for questions. If you have any further questions, obviously we have our Discord channel. if you, for example, if you come up with a question later on, we're still around for the rest of the week. So if you find us, just come up to us, say hi, ask your questions. And with that, I'd say that's the end of the course. Thank you for sticking around to the end. And enjoy using work graphs and the work graph playground.
All right, thanks.